sorry. Our goal, like I said, is to work with the natural base for today. These are exponential equations, so you're going to have some growth and you're going to have some exponential decay that we're going to have to talk about. All in all, though, you'll see that all of these behave in an asymptotic fashion, which means that we get an asymptote as our graph approaches x on the positive end or on the negative end, depending on the type of graph we're talking about. All right, so I did say today we are talking about E. It's not just a letter. It's actually named after a mathematician named Leonhard Euler, but depending on who you have at Duquesne, it might be Euler. This is called a natural base. So today we work with E. Fun facts about E, the natural base. That's a mess. That's not supposed to look like that. I don't think it looks like that on your copy, does it? Okay, good. So I fixed it on yours, but not on mine. All right. We talked about, little throwback, a couple days ago, we talked about this equation. This is purely for your visual entertainment. You need not write this down. We talked about this formula for compounding interest. And this formula is strikingly similar to what you see written on your paper there. This is supposed to be 1 over n. 1 over n. And we use this formula when wording in a problem indicates that we would compound interest monthly, weekly, daily, every hour, every minute. When there was like a number of compoundings we could figure out. To be honest with you, however, we could compound interest every minute, every second, every half a second, every half of a second. We could actually compound interest continuously. As our number of compoundings increase, all of those numbers would get bigger. All of our n values would get larger and larger and larger. In other words, as n approaches infinity, this actually approaches a constant, this 1 plus 1 over n. This business that I circled in here. It does actually approach a constant, and that constant is the letter E. It is the Euler number. It is the natural base. It is about 2.72 is what you really need to understand about E. Now, it's about 2.72 because I did skip over an important piece of information in this little box here. Do you see that E is an irrational number? It's crazy, like an irrational individual. An irrational number, can anybody give me a definition for that? What makes a number irrational? Go ahead, Didich. True story, it cannot be written as a fraction. Characteristically, what does the decimal look like? Yeah, the big kid word for that is non-terminating. So it's a non-terminating decimal. The decimal does not stop. What else does it do? Because we do have numbers that we could write as fractions where the decimals don't stop. For instance, like 3 1/3 would be 3.33333333333. That decimal goes on and on and on. It doesn't stop. But E doesn't do that. What do you think, Lauren? You can graph it. It is still a constant. It would be a horizontal line if we graphed E to the first. So we can still graph it like a regular number. Pi you could graph. It's just a horizontal line at about 3.14. So you could graph a constant. I'm talking more about the decimal. So Brendan said it does not stop. That is one characteristic of an irrational number. Think about like other irrationals you might know about, like pi, square root of 2, Christy. Yeah, it doesn't repeat. There's no pattern. That's what makes it sort of, in my mind, how I remember the definition, irrational. It's crazy. You don't know what's coming next. So the decimal is non-terminating and non-repeating, and that is true for E. So I wanted to take a minute and show you how to get E on your calculator. If you want to see E in all its glory, you're going to take your calculator out, you're going to turn it on, and the back half of this chapter takes us from studying exponential equations into studying logarithms. E is actually conveniently placed on a log button. It's on the logarithm that pertains to base E. It's called the natural logarithm, ln. And do you see the E right above ln, and ln is right next to 4? If you want to see E out to more than 2 decimal places, you're going to press second and the LN button, and then you can raise that to the first power. That would give us E. Press enter. There it is. Like I said, about 2.72, but it is an irrational number. It behaves a whole lot, visually like pi in its decimal. Questions about that? So you know how to find E on your calculator now? And we know that E is more than just a letter. It's now a number. Before I get too far into doing some calculations with E, I wanted to review properties of exponents with you. So all in all, we are going to review properties of exponents because they're going to be huge when we go to study logarithms. So we're going to spend a little bit of time reviewing properties of exponents. We're going to do some calculations and graphs with E. And then we're going to talk about continuous compounding of interest. For right now, I want you to do this. I need you to review for me what you have come to understand about e to the 6th times e to the 3rd, 18e to the 6th over 2e to the 4th, and part C, the quantity of 4e to the 3x squared up. You do not have to, at the very end of the problem, sub in 2.72 for e. I just want you to simplify these variable expressions. You can pretend e is a lot like x. So you're just reviewing your properties of exponents right now. Looks like you guys have a really good recollection of how these properties work. So I'm going to go ahead and just show you the answers. As I walk around the room, this is what most of you have. So really well done. If I had to pick a common mistake, however, as you know, I teach this through the years, usually part C, students will forget to square the 4. So just double check and make sure you have 16 as part of your response for C. You guys did a nice job. Okay, did anybody not get any of these that, maybe I didn't see on your paper and you don't know what you did wrong? Anybody have any questions about this? No? Okay, the next set of exercises you're also going to go ahead and take care of for me. It's actually a little bit of an opportunity for you to practice getting values of E on your calculator. So right now you're going to use your calculator to evaluate the following expressions. Round to 2 decimal places, that'll be fine. We're going to do e to the -2nd, so you're going to throw that in your calculator real quick for me. And then I need you to evaluate e to the 0.3 power. So you can go ahead and take a second to do that also. As I walked around, I saw this one. About 0.14 is what I was seeing as I walked around. This one here, you could use your approximately symbol, about 1.35. Okay, now this example, such a nice segue into our opportunity to graph these equations with E. Please notice that we can still have exponential growth and exponential decay expressed in terms of E. But you're probably saying, sitting in your seat, wait a second, Mrs. Lucas, how can we get decay? 2.72, that's a number bigger than 1. And according to what we've come to understand the entire chapter so far, when you have numbers bigger than 1 as your base, you get exponential growth. Now, if you think about it, you can manipulate the exponents a little bit to swap out the value of your base to be a number between 0 and 1. And you just did it. If you take a look, when we had a negative exponent in example 2, you had a negative exponent, we actually got a fraction for our answer. So you could convert your E value down to be a fraction, a number that is between 0 and 1. However, when I had a positive exponent, I ended up keeping my answer there as a number that was bigger than 1. So this is our next slide. We could still have exponential growth and exponential decay with a base of E, but you got to look at the exponent to figure out which one's which. If your exponent is a positive number, just like in the example back here, when your exponent was a positive number, you got a B value ultimately that was going to be bigger than 1. That's going to be an exponential growth function. When your R value, the rate, is a negative number, that's going to be where you're going to end up using the upstairs downstairs rule, and your base is actually going to be a number between 0 and 1, indicating some sort of decay. Again, the equations we're going to spend time graphing sort of look like that. You still have y equals a, so that'll be your initial amount. That's still your y-intercept. That part hasn't changed. This time around, we're going to have e raised to the rx power. So that's like your b to the x that we talked about in the last couple of sections. All right, so we're going to go ahead and graph. And let's take a look at part A. It says graph this function, and you're going to lean on your calculator primarily to get the points for this, to be very honest, with the exception of the first point. What's the y-intercept of this graph? Tyler, it is 2. How did you know that? It is the a value. Nice job. Okay, I have a question for you, my very smart Period 4 Honors Algebra 2 class. We just talked about the r value being positive and negative, and how that affects your function ultimately being exponential growth or exponential decay. Take a look at the r value in this equation. My question to you is this. Is this going to be exponential growth or exponential decay? What do you think, Grace? It is growth. How did you get that? Yeah, when you say it, you know, the r value, yes, that 0.6 in there, that rate is ultimately positive. So we are going to get exponential growth. Outside of the y-intercept, you're going to need your calculator to get a couple more points because of the irrational base there. So we're going to go ahead, press the y equal button on our calculator. Oh, look, I still have it in from last period. That's nice. You have 2 times e raised to the 0.6x power. And then you're going to press the graph button. I have my window in Zoom Standard. To get the actual points, it's not a bad idea to go out to the table. We could see, you know, in addition, by looking at this graph right now, I could see that what Grace predicted is correct. As x increases, so do my y values. This graph goes up. It is totally exponential growth, so good job. We can go to our table to sort of verify this pattern with growth. I, for fun, scrolled out to like 17, I guess, last period. Look at how big it got. 53,806 by x equals 17. Pretty tremendous growth. However, as we get back towards the origin, that rate of growth isn't quite so dramatic. See, I'm already back at 8, and I'm already from 53,000, I'm back at 243, so you can see that the trend there was pretty drastic. However, as like I said, scroll back through the origin, not as drastic. You know, in between 4 and 5, I'm only moving up like 18 values there, so that's not too bad. And then even back before the origin, there's my y-intercept, so you can plot that point if you haven't done so already. As I head in towards negative land, for my x values, you see that I'm getting very, very, very close to what number? 0. Good job. There's our asymptotic end behavior that we were talking about. You do have a horizontal asymptote for this graph at y equals 0. So you draw in your asymptote as y equals 0. I think it was like 1 comma 3.6 was one of the points, and then it goes over to 2 and up to 6.6. That would be off your graph. So that's a pretty good graph for this particular function. Now you do have to identify your domain and range. I do know that a couple of you skipped this portion on your homework assignment. Please don't skip that part. It is important. It tells me a lot about the way you come to understand exponential equations. Hey Jake, I see you got the answer already. What do you got? Good. Good. Well done. Questions about that? All right, now you get to try. Part B. That's all yours. Oh, this would be the first, when you grabbed this when you walked in, right up top there. That's all yours. Now, you're probably saying, Mrs. Lucas, there's a translation in this one. This one moves down 2 spaces. Don't I need a parent function? We're not going to worry about that when there's E in there. You don't have to worry about getting a parent function and then moving it down 2 spaces. That's only for when we were doing exponential growth and exponential decay that didn't involve the natural base. So you don't have to worry about that when you see E in the problem. You can if you want to, it's just not what I was going for in this particular section. All right, so as I walk around, you guys did an awesome job with that. Kudos to you, you're catching on pretty quickly. I do say everybody has their asymptote drawn in as a dashed line. Don't forget to label it. Y equals -2 is where this graph levels off. You'll notice that the y-intercept doesn't correspond to an a value here, and that's again because this graph has been translated. I can see it's translated in two ways. I see that, and I mentioned it already, it was moved down 2 units from maybe where a parent function would be. Can anybody look at the equation? I just want to see what you grabbed from yesterday with this question. It's also translated in another direction. Does anybody see it hiding out in there? You see it, Margot? That x plus 1 does move our graph as well. Very good, Margot. In what direction would it move the graph? Yeah, so if it's x plus 1, it actually moves to the left 1 unit from where the original was. That's good, good. Okay, so yeah, we're going to have to review that a little bit more with our review that starts tomorrow. Okay, last topic of the day is how would I ever use this stuff? And for that, it always leads us to a word problem. And we're going to talk about continuous compounding of interest. And I said this at the beginning of the lesson, we could compound interest yearly, monthly, weekly, daily, hourly, every minute, every second, every half a second, every half of a second, so on and so forth. We could, true story. Or we could compound interest continuously. And then you would have to think really, really hard about what your n value would be. So much so that we said as n gets very, very large, we just cave in and we use the natural base. The wording in the problem isn't going to give you something like, oh, interest is compounded weekly or monthly or, yearly or anything like that. It's going to say in the problem, interest is compounded continuously. You will look for that word continuously in the problem, and then you will know to use this formula instead of the one that we used yesterday. Here's how I remember this formula. It's a brand of shampoo. Let's see if you've heard of it. It's called Pert. Have you heard of Pert? You have? No way. I thought it was it's like the original 2-in-1 shampoo. I think they were the first people to manufacture it. But I call this the shampoo formula because it spells the formula. So it goes like this. A equals P E to the RT power. I didn't even think they made it anymore. But apparently they do, or at least you've heard of it, right, Evan? Have you seen it, on the shelves? So your grandma has it. That's great. That's perfect. Yeah, so that is our shampoo formula. I'll take you through what the letters stand for. P, you remember what P stands for? Good, Brendan. It is principal. It's the initial amount in the account. R, it is still your rate. It's your interest rate, written as a decimal. P is, again, your principal. And A is ultimately the amount in the account after T years goes by. So our wording in the problem that we're going to pay attention to in order to use this formula is continuous compounding of interest. We wouldn't have a value for n to use the other formula, so we have to use this guy. So I'm going to do part A, and then you're going to do part B. So let's read this together. It does say you get to deposit, lucky you, $3,500 into an account that pays 4% annual interest. Oh, boom, there it is. Sorry, I got excited. All right, it is compounded continuously. I'm sure that was fun for the folks watching at home. Whoa, why's my screen? Sorry. Okay, so compounded continuously. What is the balance after 1 year goes by? What we're going to go ahead and do is use our continuous compounding of interest formula. So we have our A equals PE to the RT, PERT. The principal in the account, $3,500 money bags. All right, then we have E raised to the rate times time. Your rate has to be expressed, again, as a decimal. So 4% is 0.04 times my time, which was 1 year. If I simplify that exponent a little bit, I get 3,500 times E raised to the 0.04 power. And then again, to get this, it's going to be an approximation because E is, after all, an irrational number, and anything I do with it, I will have to round. I'm going to go to my calculator and figure this out. So 3,500 times E to the 0.04. Woo! $3,642.84. About. That's a good, that's a very high yield. I wouldn't anticipate that in real life, not to disappoint you. But I think, like I said, I made like 7 cents on my savings account last year. And I have a decent principal. I save my pennies. All right, part B is all yours. Hey, Bree, Destiny calls on you. What did you get? Yes, very good. Could you hear her? She was right. Can you say it one more time, Bree? Yes, that is correct. You forgot to change your T. If you got 5,100 in there somewhere, chances are you made your T1 instead of T3. Should be 3 when you plug it in. Okay. Anybody have any questions about our lesson today? Because that is the last bit of new material you will see on your test on Thursday. No questions? It is a halfway chapter test, yes. That is a nice way of putting that. Yeah, we studied 2 function families in this chapter, exponentials and logarithmics, logarithmic equations, so logs. So the first chapter is exponentials, second half is logarithmic. What's up? Okay, so you do get your review assignment tomorrow in class, but I have 5 minutes, that's a lot of time in Lucas Land. You have blanks in your notes, true story. Just due to the patchiness of the way this packet came back from the copy center, you do have a couple of blanks. I'd like you to start reviewing right now as we speak by filling in a couple of those blanks. You could check them with a neighbor, or you know that I've uploaded the PDF files. All of the notes are always all done on Blackboard. So if you don't get a chance to check with a reliable friend, you can always check with Blackboard. Make sure your notes are accurate. So I would like you to take some time right now to wrap up this first half of Chapter 7 by finishing up those notes. And then if you have any questions,